Any questions on the hypergeometric functions? And we introduce the integral representations. As I said, the integral representations are very convenient. I mean, you can obtain the relations between various. I mean, there are only two independent solutions to that equation, but you can expand around z equal to 0, around z equal to 1, and z equal to infinity, and how you relate these different expansions, right? That is much more easy to see it from this integral representation. Yeah. Is there any question on the integral representation? I mean, there are a lot of things to say about it, but I obviously I don't have any time because today and Friday is the last day. So I will try to, because I'll have to omit a lot of things from here. I mean, but perhaps you should try to read, during the break, Christmas break, all these various properties they give, the various relations between different hypergeometric functions, etc. Try to read it. I mean, it's you can prove them. I mean, all the proofs are given, and I just don't have time to go through that. To give you an example, there is one of the relations is what happens. Again, this is. I mean, I will not prove it, but it's more or less. You have this relation. Let's see. Yeah. For example, if you take, so the f satisfies the equation z times 1 minus z d2 u by dz2 plus c minus a plus minus abu equal to 0. And f(a)(b)(c) z is the solution which is analytic at z, near z equal to 0. Is analytic near z equal to 0. So this was the definition of f(a)(b)(c), and it's also normalized so that at z equal to 0 it's 1. You normalize it like that. Okay. Now you can ask what happens if you take df by dz, right? Well, this is also going to be analytic near z equal to 0, right? Because the derivative of an analytic function is again analytic near. So this is near z equal to 0. But what you can do is that just take a derivative of, to obtain this. You can express this again in terms of hypergeometric function. Okay, this quantity. And okay, let me just show this. So suppose I start from this and take it. So remember, this is f. F with these arguments. I'm not. This satisfies this equation, right? Where f is this f. Now let's take a derivative of this entire equation. So you'll get one term will be simply z 1 minus z d3 f over dz2, which I can write it as d2. So let me call this something. Let's call it g. Okay, g is equal to df by dz. Then this is d2g over dz2, right? Because 3 derivatives are the same as 2 derivatives on this, right? Then you will get a term which will be a derivative hitting here. So that will give you so minus what is it? 1 minus 2z, right? When the d by dz acts here. After all, this is z minus z square. So derivative of that is that. And d2f by d2f by, so which is the same as dg by dz. Right? I want to write everything in terms of g. Then here, so then from here I will get again 2 terms. When the derivative hits here, I will just get dg by dz again. So it's c minus a plus b plus 1 z times dg by dz. So that is when the derivative hits here. But when the derivative hits here, I will just get nothing. It will be just g. So you get here plus or minus a plus b plus 1. Derivative hits there, so that's just this one times g, because df by dz is g. And then finally here, you just get minus ab times df by dz, which is again g. So minus ab g, right? ab are constant, so derivative doesn't hit here. So that's equal to 0. And now we can again put, you see, it's again of the hypergeometric form, because look at the coefficient of dg by dz is again a linear function of z, right? and the coefficient of g is a constant again, just like here, right? So it's again a hypergeometric equation. But now if you combine all the things, the coefficient of dg by dz here is, let's see, the constant term is c plus 1, right? This is c plus 1. And the linear term in z is a plus b. So let me write it like this: a plus 1 plus b plus 1 plus 1. Because you see, you have a plus b plus 1 plus 2, because there's a minus here. I take it, so this is minus. I take out a minus. So it's a plus b plus 1 plus 2, which is a plus b plus 3, which I write it like this in a suggestive way. And look at the coefficient of g. So that is minus. There's minus in both. You get here g times, you see, what is it? ab plus a plus b plus 1, which is a plus 1 times b plus 1. You see? So it's the same hypergeometric equation, except that a, b, and c have been replaced by a plus 1, b plus 1, and c plus 1. Right? So the conclusion from this is that the df by dz, which is g, is proportional. So f, a, b, c, z is proportional to f, a plus 1, b plus 1, c plus 1, z. You see, why can I say that? I mean, all I know is that g satisfies a differential equation with a, b, c replaced by a plus 1, b plus 1, c plus 1, right? Now, this differential equation will have two solutions. Say near z equal to 0, when I expand, it will have two solutions. But the one which is analytic is this one, right? The one which is not analytic is the other one, the second solution. Okay? So the one which is analytic is this one. So I mean, a priori you would have said that g is some linear combination of the analytic solution plus the other one, right, which is non-analytic. However, I know that df by dz is analytic. So the g must be, I mean, this g must be the analytic one, not the other solution. No combination with the other solution is involved there. Because if we combine with the second solution, it will be non-analytic. Okay, near z equal to 0. So you conclude that. And now how you compute the constant? Well, just look at the z. So this is equal to some constant, say k times this. You can determine this k by just studying at what happens at z equal to 0, right? So this one, remember the expansion of this was f, a, b, c, z was gamma a plus n, gamma b plus n over gamma 1 plus n, gamma c plus n, and then you just normalize it to make it 1, gamma c over gamma a, gamma b, right? This is expansion, z to the n. Now I take a derivative. So, and then after taking derivative, I want to put z equal to 0, right? So the only term which is relevant is z to the 1. Higher powers of z will disappear, right? When I take derivative and then set z equal to 0. So all I need to look at is what is the coefficient of z to the 1 term here. So this expression is, okay, first 0th power is 1. I mean, that's how I normalized it. Then you get here gamma a plus 1, so n equal to 1. A plus 1, which is simply a, I mean, gamma a plus 1 divided by gamma a is a. So it's a. Similarly, gamma b plus 1 divided by gamma b is b, and this divided by that is c. Okay? And then you have gamma 1 plus gamma 2, which is again 1. So this times z. Okay? So df by dz, and then set z equal to 0 is simply ab divided by c. So just evaluate both sides at z equal to 0. So this is simply ab divided by c. Okay? And whereas on the other hand, this hypergeometric function always is normalized to 1 at z equal to 0. So that tells me that k must be equal to ab divided by c. So this k is simply ab divided by c. And this is then the equation. I mean, this you get. The derivative of f is again some constant times f with the argument shifted by 1, a, b, c shifted by 1. Now suppose I look at now you can keep doing it, right? You can keep applying more and more derivatives. So if I apply dn f by dzn a, b, c, z, what's going to happen? You see, at each time I take a derivative, this increases by 1, right? So when I do n times, it will increase by n steps. So this will become f a plus n, b plus n, c plus n, z. And what about this constant? I mean, so next time when I take a derivative, then this constant will be a plus 1 times b plus 1 divided by c plus 1, right? The next time it will be a plus 2, b plus 2 divided by c plus 2, right? So this is going to become the product a up to a plus n minus 1, right? Which is actually gamma of a plus n divided by gamma a, okay? And similarly gamma of b plus n divided by gamma b, and here it will become gamma c divided by gamma c plus n. So n derivative of f is simply again this constant times f shifted, where arguments are shifted by n units. So you can find all sorts of relations. I mean, many relations you can obtain by starting from this integral equation. By the way, that integral representation is called the Euler formula. Okay, this is called Euler. Euler must have been the first one who did that. So okay, so Euler formula, and using that formula and making various changes of variables, you can get again lots of identities. Right? But I mean, I will not go into all that. It's all in the many of the identities are given here, but not all. If you want to study, get all the identities, you must look at some, this mathematical, handbooks and so on, which have huge numbers of identities for all these functions are given. But you should be able to derive all of them by using these techniques, which are given here. Yeah. So then there are some special cases of the hypergeometric functions, where hypergeometric functions, that's the infinite series, right? When I go expand around z equal to 0, there's an infinite series. But for some special cases, that infinite series collapses to a finite series. Finite. It becomes a finite polynomial. And to take some of the examples, again, let's look at, so for example, so remember what is let's again write down the series solution, A, B, C, Z. This is gamma A, gamma B, divided by gamma C, sorry, other way around, right? Gamma C, gamma A, gamma B, gamma A plus n, gamma B plus n, and z to the n. And this goes from n equal to 0 to infinity. Now, in some special cases, it might happen that this series collapses to finite number of polynomials, finite number of things. For example, let's say, suppose I take b equal to c, okay? In which case, just to simplify, this is not necessary. If b equal to c, this cancels with that, right? Similarly, this cancels with that. And in that case, the series simply becomes 1 over gamma a, n equal to 0 to infinity, and you have gamma a plus n divided by gamma 1 plus n z to the n, right? When b is equal to c. But furthermore, now you see, I can further take a situation. Suppose a was a negative integer. Suppose a was equal to minus m, okay, where m is some positive integer. Okay, so then what's going to happen? This is gamma of a negative integer. So this is infinite, right? So actually, so 1 over infinity. So the whole thing is 0, unless this also becomes infinite. You see. So when can that become infinite? So a is minus m. So this is gamma of n minus m, right? At the top, here is gamma n plus 1. So whenever n is less than m, less than or equal to m, this is also a negative integer, right? So in those cases, I mean, this is infinite, that's infinite, right? So you get a finite quantity, right? You can, yeah, you can get a finite quantity. However, the moment n is greater than m, this is positive. So this is finite, whereas here it's 1 divided by infinity. So it is 0, right? So therefore, this series truncates, this goes only up to m, right? So in fact, we can write down like this. So gamma a, and you can, So, I mean, the one way to do this is using that. I mean, don't take. Don't put. So keep it a, because I have to not take the limit. I have to take the limit. You see, a goes to minus m. I mean, a equal to minus m. It's not very well defined, right? You have to take the limit a goes to minus m, and for this you can use this this famous thing. I mean, this one of the equations that we wrote down. Gamma of a, gamma of remember z. Or x or something, let's call it x, gamma of 1 minus x is equal to pi divided by sine pi x, right? This was one of the conditions or equations we derived for the gamma functions. So using this, I mean, what is the use of this? You see, the use is that if one of them is negative, the other guy is positive, right? One of the arguments, say this argument is suppose negative, then this argument is positive, and vice versa, right? I mean, okay, let's say negative, let's say minus 2. For example, suppose this is minus 2, then, I mean, not always. If x is between 0 and 1, both are positive. But say, take x negative. If x is negative, this is positive, right? So now that's what I want to do. I want to convert this negative guy. I mean, a finally is going to become minus m, right? So a is something negative. I want to convert this to a positive guy, so I can use this. So this is the same as, gamma of 1 minus a. You see, I mean, I take down here, and then I have to, so this 1 over gamma a, right? So this becomes sine pi a divided by pi. Okay? I mean, this factor. Same way, this factor becomes 1 over gamma of 1 minus n plus a. Okay? And then you get here sine pi n plus a, okay, pi. And then there is a 1 over gamma n. That is no problem. That is always, there is no problem with the gamma n. I leave it as it is. Now I can start taking the limit, because first of all, you see this guy, these two cancel, right? These two sine, because the sine pi of n plus a is the same as, I think, minus 1 to the n times sine pi a, right? Minus 1 to the n. I mean, minus 1 to the n. So this is the same as sine pi a times minus 1 to the n, right? Okay. Now sine pi a cancels, pi cancels. And now you see I can take the limit, a goes to minus m. If a goes to minus m, this becomes gamma of 1 plus m, right? Now you take the limit, a goes to m, minus m. So this becomes gamma of 1 plus m. And here it becomes 1 minus gamma of m plus 1 minus n, right? A is minus m, so that adds up. And then you have 1 over gamma n plus 1 times minus 1 to the n, you see. See, now there is no problem. I can take the limit. I mean, because each of them is finite. You see. Huh? So this is the right way of doing it. Instead of blindly doing, I mean, if you just do it, it doesn't make much sense. No, you have to take the limit, approach a equal to minus m. No? But doing so is better to convert it into positive arguments here by using this identity. Okay. The crucial point is that this cancels. See, that's the point. I mean, this is what was giving you divergence. You see, if you look at this expression, what was telling you that when x is negative integer, this is divergent? It was this factor. This is all the divergence is captured here. And the important point is these divergences cancel when you write it like that. Huh? Okay. But now you can immediately see what is this. I mean, this expression. So what we have is this n equal to 0 up to m. You see, because you can immediately see when n is greater than m, this becomes either 0 or negative, right? Say when n is equal to m plus 1 or m plus 2 and so on and so forth, this becomes, the argument of this gamma function becomes 0 or negative integers, right? But that means this is infinite, right? So all these coefficients are 0 then, right? That's why it truncates up to m, this, right? Because the rest of the coefficients are 0. Okay. And so this is, but this, we know what it is, right? I mean, what is this? This is factorial m, right? That is factorial m minus n. This is factorial n, and then you have minus 1 to times z to the n, minus 1 to the n, z to the n, m equal to 0, n equal to 0 to n. This is just the mcn. This coefficient is mcn minus 1 to the n, z to the n. Okay, so this is 1 plus z to the power of m. 1 minus z to the m. Yeah, it's a very so this in this particular case, this hypergeometric function when b is equal to c and a is equal to minus m, this entire thing is simply 1 minus z to the m. So things like that. I mean, you know, there are this. Yeah. I mean, more generally, I mean, if you don't take a equal to minus m, already from this expression, you see that this is nothing else but let me see, 1. This is 1 minus z to the power of minus a. You remember when we I think a few days back, yes, last time I tried to expand the expansion of this guy, right? This was exactly this gamma of a plus n divided by gamma, if you remember. It was this expansion. I mean, you just take n derivatives of these guys. I mean, n derivatives of these guys, and you know, when you make a Taylor expansion at z equal to 0, you make a Taylor expansion and you find these are the coefficients. You just take n derivatives. I mean, what is the coefficient of that? Is 1 over factorial n times n derivative of this function evaluated at z equal to 0. And when you take n derivatives, you see you get a times a plus 1 times a plus 2, right, all the way up to a plus n minus 1, and that is this factor, gamma of a plus n divided by gamma a. So this more generally is that, but for a equal to minus m, this simply becomes 1 minus z to the m. But I mean, one has to be a little careful when you, I mean, what I'm saying is that the correct way to do this, when you take the limit a equal to minus m, is to, you know, go through this procedure. Okay. All right. So then there are many relations, but I'm not going to go through that. Now let me say the following thing. In the first, I mean, the third chapter, you remember we studied these classical polynomials, right? We had Hermite, Laguerre, and Jacobi polynomials. These are 3 basic classes. Then special cases, Jacobi polynomials were Legendre polynomial and so on. But Jacobi polynomial was sufficiently general. Many of the interesting cases are inside the Jacobi polynomial. So it turns out Jacobi polynomial is just a particular case of hypergeometric function. Okay. So to show this, I can erase this, all this. So to see this, now I don't have the, I mean, I don't know if you have the third chapter with you, but you remember we had this Jacobi polynomials, which comes with 2 parameters, right? I think we were calling it mu and nu. Now in this chapter, somehow for some reason they call it alpha and beta, but it's the same thing. So it was, the equation was, so we had p alpha, I mean, sort of nu mu, I'm calling alpha beta here, just to keep this notation here. It was, and I think there was an n. So this satisfied the differential equation 1 minus z square d2 u by dz2, u being this p, plus beta minus alpha plus beta plus 2 times z du by dz, and then plus n times n plus alpha plus beta plus 1. Okay. This was the equation that this p was satisfying. Now, of course, we can, I mean, here this was n was an integer, right? But we can generalize it. we can just put an arbitrary number lambda. Okay. But this is like a hypergeometric equation after all, right? Instead of z times 1 minus z, here is 1 minus z square. So if you look at the singularities, because when you have to divide this, right, by 1 minus z square, the singularities at z equal to +1 and -1. And of course, z equal to infinity will be there. So here, in this thing, the singularities are at z equal to -1, +1, and infinity. Whereas in the hypergeometric case, the standard hypergeometric equation that we wrote down, we chose the singularities at 0, 1, and infinity, right? But that's very easy to do. I mean, you just want to map these 3 points to these 3 points, right? And that is simply done by taking z goes to, let's see, maybe, for example, 1 minus z by 2. 1 minus z by 2, if when z is equal to +1, this becomes 0. When z equal to -1, this becomes 2 divided by 2, which is 1. So actually, by this map, you're taking this guy here, this guy there, and infinity goes to minus infinity, but it doesn't matter. Infinity and minus infinity are the same. All the points at infinity are the same, right? So this is this map. If you do this map, then so let's say z equal to is that correct? Yeah, z equal to 1 minus z prime by 2. No, other way around. So z prime equal to 1 minus z by 2. Yeah. So let's do this. So then this expression, I think we have to just rewrite it. So so if I invert it, so it becomes 2z prime equal to 1 minus z, which implies z equal to 1 minus 2z prime, right? Is that correct? Z prime equal to 0. This is 1. Z prime equal to 1. This is -1. That's correct. So if I substitute this, actually, why am I doing this? It's 1 minus z times 1 plus z after all, this object, right? So 1 minus z is 2z prime. And what is 1 plus z? 1 plus z is 2 minus 1 minus z, right? So that is 2z prime. So it's 2 times 1 minus z prime, as expected. It should become z prime times 1 minus z prime eventually, right? The two singular points in the z prime coordinate. And the d by dz will become -2 by, so what is dz prime? d by dz? That's equal to, from here, is the same as -1/2 d by dz prime, right? Yeah. So you do this, so this 4 factor of 4 cancels, and you just get d2 by dz prime square. Okay. Then here you'll get plus beta minus alpha, and then you get here minus alpha plus beta plus 2 times z, which is 1 minus 2z prime. And then du by dz, that gives you -1/2. So this becomes -1/2 d by dz prime u. And then the last one remains as it is, plus lambda times u. Okay. So it's again of the hypergeometric form, right? Because this is, after all, a linear function of z prime, and that is a constant. So we can now read out from there. Now we just have to just keep this z prime equal to 1 minus z by 2. Okay. So by rearranging this, you get, let's see, the constant coefficient now becomes, it's a little bit of work here. So beta cancels. You get a -2 alpha with a 1, -2 alpha plus 2, and the 2 cancels. So you get here. So I write it as plus 2 plus 1 minus alpha, right? Plus alpha minus 1. Sorry, plus alpha minus 1. Is that, I mean, am I making a mistake? I mean, this beta cancels. But I'm taking this 1 here. Beta cancels. Alpha adds up, so minus 2 alpha, and there is a plus 2, minus 2. Sorry, it's plus 1. Sorry, plus 1. Okay. And then the z prime part, that comes with a minus, so altogether minus. These 2 cancels. So you get here minus alpha plus beta plus 2 z prime du by dz prime, that is this term. And here is z prime 1 minus z prime d2 u by dz prime square. And then finally that. Plus, yeah, lambda should be negative. So I should, so this becomes plus. So I can write it as minus lambda times alpha plus beta plus lambda plus 1, right? I just put here minus to bring it into minus, because it was minus a times b, that form. So let's see if this works. So this should become the C, right? This is C. And let's say one of them I call A, other I call B. And here, this is supposed to be A plus B plus 1, right? Is it correct? A plus B plus 1. So this is A plus B plus 1. So the solution then is just F A, B, C. So it's minus lambda, alpha plus beta plus lambda plus 1. C is alpha plus 1, and z prime, but z prime is 1 minus z by 2. So the claim, so therefore this is simply P alpha beta lambda is equal to that. I mean, this is one of the solutions. So this solution is a solution which is analytic at z prime equal to 0, which means which is analytic at z near z equal to 1. Yeah. Okay. Now again, I think you should be able to show. Okay, I will not that this series. I mean, if you just by using the sum formula for this series, because after all, you know that when lambda is equal to n, this is a finite polynomial, right? So it should happen again like what I discussed before. For lambda equal to n, positive n, this should, again, this infinite series should truncate for the same reason that I discussed before, but I will not repeat now again the same thing. It should again truncate. So yeah, you just write down this power series. It's 1 over gamma minus lambda, gamma alpha plus beta plus lambda plus 1. And gamma alpha plus 1 times the sum, gamma n plus, I mean that same sum, gamma of alpha plus 1 plus n and gamma of 1 plus n, z to the n. And something should happen when lambda equal to positive integer, because this is infinite, so this sum will truncate for the same reason before. So this is, yeah. Of course, given this differential equation, there is another solution also, right? I mean, this was the analytic solution, right? But there's another solution which, remember, it went like z to the power of 1 minus c. So z being z prime to the 1 minus c times another hypergeometric function, right? That will be another solution. Okay, that solution. So that solution again will be a solution of this equation, but it will not be a polynomial like that. It will have singularity, right? Because it goes like z prime to the 1 minus c. So it will have a singularity near z equal to 1. So that's the two solutions. Okay, now you can specialize to the case. I mean, Legendre is nothing else. Legendre was just obtained by choosing alpha equal to beta equal to 0, right? So that means for the Legendre, you just set alpha equal to beta equal to 0. So that's simply f minus lambda and lambda plus 1, 1, and 1 minus z by 2. Once again, for lambda equal to positive integer, this becomes a polynomial. finite polynomial. Otherwise, it will be infinite. For arbitrary lambda, it will be infinite series. Okay. I just want, this is just to show that, I mean, how hypergeometric functions are related to almost everything that you have seen so far. I mean, this is Jacobi polynomials. But now the other thing that I wanted to do, yeah. Mm-hmm.
Lambda is minus beta, then
lambda is minus beta. So lambda is minus beta, so that disappears. This becomes gamma of alpha plus 1, this cancels. And here lambda equal to minus beta, so again this cancels with that, right? So it will not truncate unless, of course, lambda equal to the integer, right? Yeah, if you take lambda equal to minus beta, so then all of this cancels with that, this cancels with that, so you just have this sum. But in that case, probably you can write it as minus lambda. I mean, that formula which I wrote down, this is probably 1 minus z to the power of maybe lambda or something like that. Huh? Yeah, lambda, exactly. Correct? Yeah, this expansion in that case, lambda equal to minus beta, is just that. But if lambda is a negative integer, or if it's not a positive integer, this is not a finite polynomial, right, when you expand it. It's only for lambda equal to positive integer. It will be. Actually, that is what gives you the, I mean, you see, typically what happens, I mean, in quantum mechanics and so on, you get some differential equation, right? This will be like the Schrodinger equation, which, which will appear. Now, you see that this will be the kind of eigenvalue, right? I mean, this will be kind of eigenvalue equation, right? These numbers, this lambda says related to eigenvalue of the Hamiltonian, for example. Huh? Now, if you choose arbitrary lambda, then this will be an infinite series. Okay, and that will start having divergences at. I mean, here this is an analytic function near z equal to 1. But what about z equal to 0? You have to also check z equal to 0. What happens there, right? So if you want to have in both, I mean, you want to have regularity in both points, both endpoints, z equal to -1 to z equal to +1. In the original variable z, in the z prime variable, it is 0 and 1. Between 0 and 1, you want regularity on both sides, and that essentially picks out this. I mean, if the polynomial truncates to a finite polynomial, of course it is going to be analytic on both. Any finite polynomial will be analytic at any finite value of z. I mean, we don't care about z equal to infinity because that's outside the domain. Because I mean, Legendre, for example, appears. Why the z between -1 and +1? Because z is cosine theta. You know, in this three-dimensional problem, you have the radial coordinate r, then the angular coordinates theta and phi, right? So theta, of course, is between 0 and pi, right? Phi is the azimuthal angle, and theta is between 0 and pi. So cosine theta is going to be between -1 and +1. So you don't care what happens beyond that, no? You only want it to be regular in the real line between -1 and +1, okay? Which in the z prime variable, it will be between 0 and 1, okay? So if it is a finite polynomial, of course it's going to be analytic everywhere. Whereas if it is not a finite polynomial, this will develop a branch cut or singularity at the other next point, z prime equal to 1, you see. As we saw before that, yeah? I mean, in fact, you can see from here, this expression. So what was that? Sorry, this is not z, it's 1 minus z, right? I mean, the argument is 1 minus z over 2 to the n. So this will be 1 minus z by 2 to the power of lambda. I mean, this was z prime. So at z prime equal to 1, if lambda was not an integer, there will be not a regular solution, right? There is kind of a cut, branch cut. And that is what tells you that lambda must be an integer for the physical, I mean, the quantum mechanics problem. You want the wave function to be well behaved, right? Then this lambda has to be integer. That's what gives you the quantization conditions. Okay. But there may be other physical problems where you don't I mean, you're not looking at these kind of issues. You are really interested in singularities and things like that. No? So the more generally, you have to look at, I mean, this is the more general Legendre. Legendre functions, you call it Legendre functions because generally they are not polynomials, right? Only for lambda equal to integer, positive integer is a polynomial. Otherwise, it's just it's called Legendre function. Again, there is this is one of the solutions of that equation. There will be another solution which will have the singularity z prime to the power of 1 minus c, right? 1 minus c. Okay. So c is alpha plus 1 and alpha is 0. So actually, it's not even singular. But anyway, there's another solution which is singular at z prime going to infinity. Not at z prime equal to 1, but z prime going to infinity. There's another solution. So you choose two linearly independent solutions like that. It's described in the notes, but I will now move on to confluent hypergeometric functions because that's again a very important. Many functions. Here, Jacobi functions were related directly hypergeometric functions, right? Jacobi functions are the same as hypergeometric functions. But if you want to ask what happens to Hermite and Laguerre polynomials, they are not directly hypergeometric functions, but they can be obtained by some limiting procedure starting from a hypergeometric function. Okay? And that limiting procedure will give you something called confluent hypergeometric function. Right? And also a very important function which we have never discussed so far, the Bessel function, which appears all over physics. The Bessel functions are related to confluent hypergeometric functions. So for this reason, I think from the rest of the today and next lecture, I'll be discussing this confluent hypergeometric and Bessel functions. Of course, not in too much detail because that's really, to really discuss all the properties, you need a lot of time. And it's here we will also come across the irregular singularities. I mean, so far we have always worked with the regular singularities, right? Now, in this limiting procedure that we'll be discussing, one of the singularity will become irregular. Yeah, confluent. Okay, so now we discuss the section 19. That's confluent. Geometric functions. Okay. So let's go back to our original equation where we had the singularities at Z1, Z2, and Z3. I mean, remember, in going to the hypergeometric, we set the singularities at 0, 1, and infinity. But I will bring back the things because we're going to take limits. Okay, so that's why I want to bring it back. So, okay, one of the points I will take the 0. The singularities are at z equal to 0, and then I keep the Z2 and Z3. So I just put Z1 equal to 0, right? Before what we did, we put Z1 equal to 0, Z3 equal to 1, and Z2 equal to infinity, right? But I want to keep these two things because what I will do is I will bring them together, Z2 and Z3 together, not separately. So let's write down the equation. The original equation, it was d2 u by dz2 plus c over z. These are three parameters, 1 minus a minus b divided by z minus z2 plus 1 minus c minus a plus b divided by z minus z3. I mean, this was the same, you remember that, I mean, that was the starting point of the hypergeometric equation that we obtained, right? We had the poles, first order pole at the 3 points. I mean, just I put z1 equal to 0, that's all. And with the 3 parameters here, and the condition was that the sum of these parameters must be equal to 1, right? And let's see if it's true. C cancels when you add them up minus, oh. How come? I think there's a misprint here. Must be a misprint, huh? No, some of them is equal to 1 or 2. But in any case, this a had to cancel. So one of the signs is wrong here. Either here it's wrong or there it's wrong. Because some of these must be equal to 1. Otherwise, you will get divergence at infinity. infinity would not be a ordinary point. Huh? How come? I mean this. Sorry, I mean we have to go back to see what is that. 0. I mean we have to go back to this equation 16.1. No, yeah. No, sorry. It's written not the sum. Some of that had to be 2 actually, right? Some of that had to be 2. But in any case, I mean this a has to cancel. So there's something wrong. Either this sign is wrong or that sign is wrong. Okay, one of them. Okay, I mean let's proceed and keep in mind that one of these signs is wrong. There is a misprint here. And then yeah, and then the last term is plus AB. Now I'm not sure because the signs may be all a bit off. In various places signs may be off. Square z minus z3. Okay. U equal to 0. So this is, I mean, this should be just the equation that we started from the very beginning, 16 point whatever that equation was, 16 point, no, 16 point, where is it? 16.1. It should be from 16.1 by specializing, okay, by choosing just z1 equal to 0 and by specializing to some particular, I mean parameterizing alpha, alpha prime, etc. in a particular way. You should be able to get this. So with the correct sign. Okay. So please, I'll just leave this as a, I mean please try to do it. 1 minus c plus a plus b. 1 minus c plus a plus b probably. It must be that. Huh? Yeah. So then this will satisfy that equation. But then also please check also this term. And this term also you check. You should be able to get both these things by choosing. In 16.1 you had this alpha, alpha prime, beta, beta prime, and gamma, gamma prime. Okay. And you should be able to. I think it's the same thing because it is the same. Okay, I can tell you what one should do actually. It's the same thing because finally it is simply FABC. So it should be in the same symbol here. Just take this P symbol. You have Z1 I put to 0, but I keep Z2 and Z3. So Z2 and Z3 I don't put that to 1 and infinity. Okay, keep as it is. And then here it was the same 0, 1 minus C, and then A, B, and 0, C minus A minus B. It should be the same thing. Okay, and so just keep the Z2 and Z3 because you see in order to get from here the hypergeometric equation, what we did was we set one of them to infinity, and as a result a lot of terms disappeared, right? And that's why the final equation became simple. But don't take it infinity, so you keep all the terms which are there, and you should get this equation. Okay. All right. So what is the idea now? So now what we want is that we want to sort of bring Z2 and Z3 together, right? But in some particular way, because I mean if I just naively put Z2 equal to Z3, you see this drops out, right? So there will be no constant term. I mean no sort of what do you call without derivative term. Then this becomes a rather simple type of thing because it's an equation, a first order differential equation for du by dz, and then you can solve. It's not it becomes a trivial thing, right? So you want to bring it together in such a way that you should get something out of this. It should not vanish. So one way to do this is to, let's say, we'll take both of them to infinity, okay? But let's say I take Z2 equal to 2Z3, and then take both of them to infinity. Okay. Again, if I just do this, I mean, it need not be 2, it could be anything in particular, right? I mean, but by doing so, this is never going to be 0, right? And then if you take Z2 and Z3 both to infinity, what's going to happen? the numerator there are 2 powers of Z3. Suppose I write Z2 equal to 2Z3, right? So this becomes 2Z3, this becomes Z3, so 2Z3 square. But denominator has 3 powers of Z3. So again, it becomes very trivial then, right? So I should do something else. I should also do something more. Let's take B and say B also goes to infinity. After all, these are all parameters in the theory. So I will take B equal to Z2 equal to 2Z3 and all of them to infinity. Okay. So now this term is there. I mean, you cannot, this term is there. Okay. But at the same time, what we have done, see, both these points have been pushed to infinity. So 2 singularities have coalesced at infinity. So this is the resulting equation is the confluent hypergeometric equation. Okay. So let's do this. So when I take this limit, so what happens to this object? So this guy becomes, okay, C over Z is as it is. Here, Z2 is infinite. Z2 and B are equal, right? And they are both going to infinity. So this simply becomes +1, right? Okay. B and Z2. Whereas this one becomes, let's see, B is equal to 2Z3, and that's going to infinity. So this gives you -2, because there's a minus sign here. Yeah? So altogether this becomes -1, or C minus Z divided by Z, times du by dz. I mean, this remains the same, d2 u by dz2 plus that. And here, so if I take, so Z2 is 2Z3, so this becomes 4 Z3 square, and then so -4 Z3 cube down times Z. That is what the denominator becomes. And the top becomes 2Z3, 2Z3, 4Z3 square, and then this is Z3. So 4Z3A times 4Z3 cube. So this becomes simply -A by 2. Minus A by Z. No, sorry, this is 2. What is this? No, this is Z. This is Z. So minus A by Z. This is Z. Okay. So you get here -A by Z U. Okay. Is that? Yeah, that's correct. Okay. So you just multiply by Z to get this equation. So you just multiply everything by Z, so you get this equation -AU. This is the confluent hypergeometric equation. Okay. So idea was basically the idea was to bring the two singularities together, but in a way that keeps the non-trivial features of the equation. I mean, doesn't become a trivial equation. That's the idea. So now this equation has only 2 parameters, A and C. That's it. Because one of the singularity I've already set at 0. Z1 I already taken to 0, and other singularities at infinity. Okay. And once again, if you look at the indicial equations around Z equal to 0, in fact, let us see what kind of equation is this. There are only 2 singularities, at Z equal to 0 and Z equal to infinity. At Z equal to 0, this singularity is of the regular type, because when you divide by Z here, this is only first order pole. And this is also only first order pole. I mean, in principle, you could have also had the second order pole. That would still be regular. But here it's only first order pole, so it's even better. But at Z equal to infinity, if I want to study this, so let's see at Z equal to infinity what happens. So write Z equal to 1 over Z prime, as usual, and study at Z prime equal to 0, right? So this becomes d2 or d2u over, so again, d by dz is the same as minus, Z prime is 1 over Z, so minus 1 over Z square, which is same as Z prime square, d by dz prime. So that becomes Z prime square, d by dz prime, Z prime square, d by dz prime, and then that is 1 over Z prime. And then here you get C Z prime minus 1 divided by Z prime when I write. And then du by dz, so it's again another minus. z prime square d by dz prime. Yeah. And then finally minus au. Is it?
Z prime raised to minus 1 d by dz.
D by dz, so d by, let's see, maybe I made a mistake. D by dz is dz prime over dz, d by dz prime. But z prime is 1 over z, so that gives you minus 1 over z square, right?
Yeah, yeah.
But then it becomes minus z prime.
Which is in z prime, I see.
Yeah, z prime. Okay. So this gives you, so one term will be z prime cube, because there is a 1 over z prime here, d2 u by dz prime square. Then another term in derivative hits here, so a factor of 2. So this becomes plus 2 z prime square, because it's a cube and 1 power down. So du by dz prime. So actually, so this just adds up, right? So I can put together everything. So this is this goes out here. So there's a cz prime square. So I can put together everything here. So 2 minus c, 2 minus c z prime square, and minus, yeah, minus minus plus. So plus z prime du by dz prime, and then finally minus au. That's equal to 0. But now you can immediately see when I divide by z prime, I mean, you want to make this coefficient 1. This has a third order pole, right? Already, this is so it's not a regular singular point. And this guy also has a second order pole, you see, because z prime divided by z prime cube will be 1 over z prime square. So this has a second order pole, and that is a third order pole. So it's not a regular singular point. So at infinity, it's irregular. Okay, but at z equal to 0, everything is perfectly fine. It's a regular singular point, so we can make an expansions around z equal to 0 and get the two solutions, the fundamental solutions. So we need to look at the indicial equation. So that is obtained by simply making an expansion, right? So sorry, is there any question here? Because I'll now erase some parts. I mean, now I'll focus on just this equation. Okay. So what is the indicial equation? It was, what is it, r square, what was it, minus 1 minus a naught? Plus or minus here? Minus. Plus a0 minus 1 times r plus b. Okay. b0. Okay. Now a0 was the coefficient of the first order pole of the p, of this function p, right? I have to divide by z. And then this was b0 was a second order pole. So b0 is 0 anyway for this case, because this is only first order pole. There is no second order pole. So b0 is 0 for us, and a0 is simply c, right? Because c, when you divide c over z, that is the pole. So this is c. So equation is simply that. So the two solutions r equal to 0 and r equal to 1 minus c, which is indeed this was the case, right? Because whatever else we did, I mean, this didn't change. This one we didn't change. We just moved z2 and z3 together, both to infinity, but also at the same time b to infinity. We did all that, but that didn't touch this part. That didn't change. So that part is remained the same. So we have two solutions. One which is analytic, and other which is if c is not if this is not an integer, that would be, if this is not a, what is it? If c is not a negative integer, then if c is not equal to 0, minus 1, minus 2, etc., because then you see this root will have, the real part of this root will be greater than that, right? So this would be R1, and that would be R2, okay? And furthermore, the difference would be integer in this case, right? If C was one of these numbers. In that case, you know that while for R1 there is an analytic solution, but for R2 there is no, right? In general not, there will be logarithm and so on, okay? So if C is not one of these, then for sure there is a solution corresponding to that, analytic solution corresponding to this. So there's an analytic solution, okay, corresponding to that, and it should be again related to hypergeometric function. After all, because this equation we obtained by some limiting procedure of the hypergeometric. I mean, you expect that it should be given by the appropriate limiting procedure for the hypergeometric, right? So how do we show this? So actually, okay, you can, of course, you can write down the power series here. I mean, you know, you can just develop the power series for r equal to 0 and obtain the coefficients, the Cn, coefficient Cn, and read off from there. But the procedure adopted here is slightly different. So let me follow this procedure. Okay. So the idea here is to write down an integral representation for this equation, just like we did for the hypergeometric, right? We wrote it as an integral over some function of t, right? And so the same thing we'll do, but we will use another. So we will consider, because remember for hypergeometric what we did, we had some function, let's say v of t times z minus t to some lambda. We started from this dt, right? And then we just applied this differential operator, that hypergeometric differential operator on that, and then we try to find what kind of a v I should choose such that that this result becomes 0. The adjoint operator becomes 0. Here instead of, this is by the way is called a kernel. This is by the way called Euler kernel. So this is a kind of kernel that you use and then multiplied by some function of t, and then try to see if you can find some function of t such that the differential equation is satisfied. This is the kind of method you do. Here we'll use different thing which is called Laplace kernel, which will be, instead of that this function, it will be e to the zt. Yeah.
Does it have a name or is
Huh?
just
Sorry?
when you say kernel, does it have a name or a meaning?
Kernel. No, kernel has has some meaning, but what is the meaning kernel? I frankly don't know precisely what the meaning of kernel is. It's used in, I mean, in mathematics it's used in many different contexts. I mean, kernel is used in when you have some, I mean, let's say there is some map. There is something where something is mapped, there's some map, let's say, I don't know, some map A from one space to another space, or one variables to another variable. Then in general, I mean, this map would mean that there is every point here will be mapped to some point here, right? But it need not be one-to-one map, right? So it could be that several points or even some subspace is mapped to just one point here. It could happen, right? So in particular, suppose if this was a vector space on this side, both are vector spaces, then in the vector space, there is one preferred element, one distinguished element, which is the 0, right? 0 is a distinguished element of the vector space, right? So if this, so the image of the map, of this map, which image of the 0, which means all those points which are mapped to 0, okay, that will be a subspace if the map is a linear map, let's say. If it was a linear map, then this will be a subspace of the original space. That subspace is called the kernel of A. Okay. That is usually the way kernel is used in mathematics. Now I don't know why this is called kernel. I don't know. Maybe to say that by starting from this, you can obtain some solution to where this differential operator, adjoint operator, annihilates it. I don't know what was the origin of this word kernel here, but standard use of kernel is in this sense. So this would be the kernel of the operator A, kernel of A. Okay. So we start from the Laplace kernel. So this time we'll start, and we will see later why Laplace kernel, because we'll compare it with the hypergeometric. So here we'll start with e to the zt. Okay. Again, some contour which has to be determined later. So suppose u was of this form. So then let's plug this in here. So you will get, this time it's very simple because every time the derivative hits only the exponential, so it just brings down t. So that's much easier. So you get here z t square, right? Then you this first term. Then the second term gives you c minus z t du by dz minus a. That's what it is, right? Times e to the zt times vt dt. So this differential operator when acts on the, so this left hand side of this equation, the LHS of this equation is equal to that. Huh? Is that clear? I mean, I just apply two. Each time you take an applied derivative, this just brings down a t, the power of t. So I apply two derivatives, it brings down 2 powers of t, t square. So this becomes z times t square plus c minus z times t plus minus a. So that's the. And now I can, let's see. In fact, this is that correct? Z t square. So actually, this becomes a very simple equation, right? Because there is only one. So I can rewrite this as z times t square minus t. I mean, just combine the z terms are that, and then you have plus ct minus a e to the zt. I mean, so this is what it is. But wherever I see z, I can just replace it by d by dt. After all, right? So this becomes t square minus t. So I keep vt here. T square minus t d by dt. Okay, I'm using the partial derivative just, I mean, just because it's not acting on z. I mean, but it's really ordinary derivative, nothing. Huh? Plus ct minus a acting on e to the zt, right? dt. So this is that. And now what I want to do, I want to choose a v such that the adjoint operator acting on the v gives you 0, right? And of course, I have to worry about the boundary terms. But since this is the first order, I can keep track of both the terms. Remember, for the hypergeometric, I didn't keep track of the boundary terms. And I asked you to check the boundary. I just use the formula finally there. But this one is. So what is adjoint operator? So it's simply, okay, minus d by dt, t square minus t bt, right? That's the first term. When I just do a integration by parts, there's one term. And the other term, okay, as it is. So plus ct minus a times vt. This must be 0, that statement. And the boundary term is just that, t square minus t times vt. And the boundary term is simply vt times t square minus t times e to the zt. Yes. So okay, what is this? This again, I do the same. Maybe I should keep this equation somewhere so that we don't zt2 u by dz2 plus c minus z du by dz minus au equal to 0. A solution of that equation is simple. Just call this guy some gt, right? Then the equation is simply dg by dt equal to ct minus a divided by t times t minus 1, because t square minus t is a t times t minus 1 gt, right? If I call this whole thing as g, then v becomes g divided by that. So I just replace v divided by that. And minus sign, so I took it on the other side. So I divide by g here, and this again do the same partial fractions. So what is that? This is, let's say, write a by t plus b by t minus 1, which is, so this is the same as a plus b t minus a divided by t minus 1. So therefore, capital A is the same as small a, right? So capital A is equal to small a, and capital A plus B is equal to C, but capital A is small a, so B is equal to C minus A. So you get that. And then the solution of this equation is G of T, log of G is equal to log of A times log of T plus B times log of T minus 1. So then take the exponential on both sides. So you get G of T is equal to T to the power of A, which is small a, and T minus 1 to the power of capital B, which is C minus A. That is G, and therefore V is simply G divided by T times T minus 1. So V, therefore, we conclude that Vt is T to the power of A minus 1 and T minus 1 to the power of C minus A minus 1. That's the term. And then for the boundary term, from here you see Vt is that, and this is T times T minus 1. So this boundary term is simply T to the A and T minus 1 to the power of, this is Gt. The boundary term is simply Gt times e to the t. So Gt was that, A and C minus A e to the zt. This is the boundary term. Okay, this boundary term. So you can choose with different contours. For example, for different ranges of these parameters. For example, if real part of C is real part of C minus A is positive, and real part of A is positive, then clearly this vanishes at both t equal to 0 and t equal to 1, right? So I can choose this boundary to be, this contour to be from 0 to 1 in that range when for the real, when this is real part of this is positive and real part of this is positive. Okay, so that's one choice. So let's choose this choice. So we choose real part of C is greater than real part of A. If you want to make this real part positive, that's that. And also you want to make the real part of this positive. So this is 0. Real part of C is greater than real part of A is greater than 0. In that case, I can choose this the u of z is simply 0 to 1 dt, and then we have t to the A and t minus 1 to the C minus A. Actually, let me write it as 1 minus t to the C minus A. That doesn't matter. Up to overall, you can multiply by any overall factor, right? Some k times e to the zt. Okay. So that's the solution. That is one solution. There should be two solutions here, but this is one solution. Now, let us expand. Let's.
Which one should we look? V is the t raised to a minus 1?
Sorry?
V is t raised to a
Sorry, a minus 1. Correct. This is C minus 1. That's This V is that. Correct. Yeah. Okay. So this is the solution, and now let us. We can expand it, right? Near z equal to 0, right? This function is analytic near z equal to 0. You can see because, you get this. There's a power series expansion in z, okay, near z equal to 0, right? So this is simply 1 plus zt plus in general z to the n t to the n over factorial n, right? That's what it is. This is the expansion. So let's see what kind of a series you get. You get here, but now, so this is t to the n. That makes it, so the coefficient of z to the n, there's a k, this k which will determine. So what we'll fix the k in such a way that at z equal to 0, this becomes 1. Just like the hypergeometric function, we normalize it so that it was equal to 1 at z equal to 0. Same way we'll do that here. So this k we'll choose to do that. K times z to the n, let me write like this, n, z to the n. And then I have this integral 0 to 1 t to the power of n plus a minus 1, right? And then 1 minus t to the power of c minus a minus 1 divided by, so 1 over factorial n is here, dt. But this is the beta function, which we have seen, right? This integral. So this gives you gamma of n plus a, and this gives you gamma of c minus a, okay, and then divided by gamma of the sum of the two, which is gamma of n plus c, okay, and factorial n, of course, is gamma of n plus 1, okay, so k times z to the n. This is the result. So this function is indeed analytic. I mean, sorry, this you cannot see. You can also not see. Okay, down. Okay. So that's the expansion, and now I can choose k to make that z equal to 0. We want it to be 1, so I can just choose k to be. So choose k to be just put n equal to 0. So 1 over gamma a, gamma c minus a, and n equal to 0. So this is gamma of c. So choose k equal to that. Then this becomes normalized to 1 at z equal to 0. Yeah. So finally, so we will give it a name to such this function. So going back to this original equation, what we are saying, we are saying that of course this has one solution, because this was at z equal to 0, the roots of the indicial equation are 0 and 1 minus c, right? So the one which corresponds to 0, that's going to be analytic, provided c is not one of the 0 or negative integers. So this is that analytic solution I will just denote by phi, capital phi, and that will depend on what parameters. There are only two parameters here, a and c. So I put here a, c, z. So this is the analytic solution. The analytic solution near z equal to 0, at z equal to 0. And we again normalize it so that phi a, c, 0 equal to 1. With that normalization, we say that this is the same as that series. Okay. So this series is, so in that case, we are saying that phi a, c, z is, once you choose kappa equal to that, then gamma c minus a cancels, and you're just left with gamma c divided by gamma a and gamma a plus n, gamma c plus n, gamma n plus 1, z to the n. So this is that. This is what is called the confluent hypergeometric function. This is the confluent. Hypergeometric function. This symbol. Okay. You can now comparing this with the hypergeometric series, you can see you can realize that in fact this can be obtained directly from the hypergeometric function by taking a suitable limit, and that limit I will now indicate. So remember what was the so we had f a b c z was gamma c divided by gamma a, gamma b, summed n equal to 0 to infinity, and this was gamma a plus n, gamma b plus n over gamma c plus n, gamma 1 plus n, z to the n. Okay. Now let's take, instead of z, let's take z by b, z divided by b. So I mean, I'm describing the limit that you have to take so that this becomes that. So you take z divided by b. So of course this becomes z to the n divided by b to the n, right? Because I'm replacing z by b. And then take also b to infinity limit. Okay. So if we look at this b2, I mean this is gamma b plus n divided by gamma b. What is that? Gamma b plus n divided by gamma b. This is nothing else, b plus n minus 1, b plus n minus 2, all the way up to b, right? How many terms are there? There are n terms here, right? So I can take out b to the n outside, then this becomes, so this is the same as 1 plus n minus 1 divided by b, 1 plus n minus 2 divided by b, all the way up to 1 plus 1 over b times 1 times b to the n, right? That b to the n will cancel with this b to the n. Okay. And now I take b to infinity limit, then this just simply becomes 1. For any finite n, it becomes 1, right? So, and then you see that this just collapses to that, because you have a gamma c, gamma a plus n over gamma c plus n, gamma n plus 1, and this b to the n just cancelled with all that. So really this is nothing else but the limit b going to infinity of this hypergeometric function, fabc z over z divided by b. So this is the is a certain limit of hypergeometric function, but in a particular way you are taking the limit, no? Because you are not only you are taking the first you take z divided by b, so and then b to infinity, no? So it's in a very, very specific limit. I'm getting that. And this will also explain to you why we are choosing Laplace kernel instead of Euler kernel here. The reason is in the Euler kernel it was z minus t to the power of what was it, lambda. Lambda was a or b. So remember, I could have chosen also b. It doesn't matter, right? Because it's symmetric in AB. FABC AB was symmetric, right? So I could have also instead of, I mean this is the same as exchanging A B B A. It's no problem. So here it was, in fact, remember when we wrote it as lambda here and demanded that the z square term cancels. Lambda had two possibilities. It could be either minus a or minus b, right? We chose minus a, but equally well you could have chosen minus b. Answer would be the same. So let me choose minus b here, and then here what was the other terms? What was the t? What was the solution? I always forget this. T to the power of t to the power of a minus 1. So t to the a minus 1.
minus 1 raised to minus
Huh?
t minus 1.
So t minus 1 to
Raised to
c minus
a minus 1. Yeah.
So that's that. Yeah. This was I mean after exchanging a and b. Is that what you get? Before it was b. Is it? Before we chose this to be a, or did we choose b? I don't remember what we chose. Yeah, it should be. Yeah. Yeah, okay. I mean, yeah, indeed, if you exchange a and b, it should be this. Huh? uz equal to b. Yeah, I suppose huh? B is 0. No, we are going to take b to infinity limit, right? Eventually. Yeah. So I think, okay, this seems to be, if I'm not, minus b. Yeah, t to the a minus 1, 1 minus t or t minus 1. So let's take, I mean, there was this expression which was, yeah, sorry, and this was, we had obtained this expression which was, yeah, here it is 17.31, right? 17.31. It was originally, it was written 1 minus zt to the power of minus a, 1 minus zt to the minus a, t to the b minus 1, and 1 minus t to the c minus b minus 1, correct. So this was the integral together with gamma c over gamma b times gamma c minus b. Okay, this was the FABC z. Okay, so in order to do this, I had to remember I made a change of variable also there. I mean, initially we had the integral from 1 to infinity. Then I made t goes to 1 over t to make it 0 to 1. So this integral is 0 to 1. Okay. That is 17.31. So is this one? But now we know that A is symmetric in A-B exchange, right? So this is the same as I could just replace B by A. Here this becomes A, and that is B. Okay. So that's FABCZ. Okay. This is t minus 1. Or I can now write it as 0, 1 minus t. 1 minus t, 1 minus t. Okay. So this is the expression. So let's see now why we get something like this. And unfortunately, I erased that. But okay, so first of all, remember I have to take z to z by b. So I should just replace z divided by b. So this becomes z divided by b. Okay, and now I take b to infinity limit. Okay, but then this becomes simply e to the zt. Right? So that's why this is just that. And in fact, if you, I just erased this, but the VT we've obtained, the solution for VT was exactly that. So this is the way you can get. And this the kappa is of course that. You see, that was a constant which you had to multiply so that so that it's normalized. That at z equal to 0 it should be 1. That's now, what about the second solution? The second solution again you can obtain. Okay. So, this was the analytic solution, right? But then there should be some solution which goes like z to the power of 1 minus c. This you can again either you start from the second solution of the in the hypergeometric and again go through the same limit, right? Or you can just directly work here. Sorry, just one little comment. Although you see this series we obtained starting from that integral representation, and for that integral representation we needed this condition real C is greater than real A greater than 0. But really this I could have also obtained directly from the series solution that we know how to do series solution, right? You start from the z to the power of r, so I choose z r equal to 0, and then you just get recursion relations for the coefficients Cn, and you will find again the same answer. Okay, but in that way of doing, I'm not assuming anything. I'm not taking this condition real C is greater than real A is greater than 0. The only thing you have to say is that C should not be 0 or negative integer, otherwise this will blow up. So actually, even though this is derived from this representation, but that was just a limitation of this representation, that we had to choose this condition. But it was not necessary to choose this condition. You could directly work from there and obtain this. Right? Okay. The second solution I can again obtain from maybe the standard. We can probably let's try the same way that we obtained hypergeometric thing. So let's now look for a solution which is z to the power of 1 minus c times some v, where v is an analytic function. Because second root is 1 minus c, right? So there should be a solution like z to the 1 minus c times some analytic function of z. And let's plug that in here. So you get so du by this we have to keep doing it. Is the same as z to the 1 minus c dv by dz plus 1 minus c over z, and then d2 u by dz2 will be z to the 1 minus c d2v by dz2 plus 1 minus 1 minus c over z square. That's from there. Then a derivative acting here will give you, again I take out this here, so 1 minus c over z times this whole thing. Yeah, I mean 2 derivatives. That is okay. So plugging everything there. So plugging everything there. Have I done correctly? dv by dz. Z. So this is 2 derivatives here, and then other acting here. So 1 minus z over z times z. And then I can take out z to the 1 minus c, which is a common factor everywhere. So you get an equation d2v by dz2 times this whole thing multiplied in z. Okay. Then let's collect all the dv by dz terms. So dv by dz. Okay. So there is this thing multiplying z. So that gives you 1 minus c from here. And yeah, and then from there you get plus c minus z, plus c minus z times this, plus c minus z. Is that correct? Or am I making some mistake here? I'm just collecting dv by dz term. So there's one term which comes from the second derivative, but there I have to multiply by z. So that becomes 1 minus c. And the second term comes from already the first derivative there, but that I have to multiply by c minus z. So that's plus c minus z. I mean z to the 1 minus c I've taken out from everything. I've thrown out that. So that's that. So dv by dz, this. And then the non-derivative term, there are several pieces. One piece is from here. And that, I mean, looks like 1 minus, maybe this doesn't work, 1 minus c z square from here. But then I have to multiply by z. So that is 1 minus c square over z. And then from here you get minus 1 minus c over z again. And that's from these two terms. From this term, I'll get, so plus 1 minus c times c minus z divided by z. That is what divided by z. This whole thing is multiplying. This is all minus a. Minus a multiplying v. Minus a because just that term, the last term. Okay. Now let's see if I mean, this is again of the same form as before, right? After all, there is a z, there is a linear function of z here, du by dz. But here, there's a pole, right? Let's see if pole cancels. So if I combine these two things, it's 1 minus c is a common factor. So 1 minus c divided by z. And then you get a 1 minus c minus 1, which makes it minus c, right? And here also it's plus c times 1 minus c divided by z, so that cancels. And what is left over is this term, but there's no pole, it's just z. So it's just 1 minus c, okay? Minus 1 minus c, so c minus 1. So this last term is simply plus c minus a minus 1. If I want to write it like the same way, so minus a plus 1 minus c times v. And this c cancels. So basically what we are seeing is the v, the second solution is simply, so v therefore is analytic. We know v is analytic. And so by just reading off, you see what it is. This is phi of, let's see, a is replaced by this. So a plus 1 minus c. And c is replaced by 1, right? 1 z. Okay. Now I don't know if I have made. If there's a mistake, we'll see this answer is wrong. Confluent. No, it's 2 minus c. I made a mistake in this somewhere. This is 2. This should be 2 minus c. So let's see, a plus, where is it? So this part, this one is correct, a minus c plus 1. But here it should be 2 minus c. What is happening? 2 minus c. See how. This should be 2 minus c, and we are seeing only is 1. How? This should be replaced by 2 minus c. I mean, this is what you obtain from taking the second solution. The second solution is z to the power of 1 minus c, the hypergeometric. You get f b minus c plus 1, a minus c plus 1, and 2 minus c, z. Right? If you take the same limit, z goes to z by b, and then take the limit b goes to infinity, you get this expression but with 2 minus c. I mean, z to the 1 minus c is outside, okay, that one. I mean, this is v, but this should be 2 minus c. So I think I have made some mistake in these derivatives. Do you see if I miss something here in these expressions? Is it z square. I don't understand. This should be, this is simply that, 1 minus z over z square. Oh, unless it's adding. I mean, did I? No, not there. Sorry, here minus a. Sorry. Is it, I mean, where? Here. Here is 2 times 1 minus c. Where do you see that? Twice 1 minus c? Here there is a factor of 2. Huh? Let's see, we're looking at the dv by dz coefficient, right? So there is a 1 minus c. And I mean, somehow this must, there's a sign, I think there's something wrong with the sign. Minus c. That is plus c minus z, is it? Phi. Sorry, I mean, I cannot, what did he say? Is it 2? Is it 2 here? Sorry, I'm not. If it is 2, but is it 2? I mean, if it is 2, then this should be true. But yeah, maybe it is a factor of 2, because I'm in fact surprised why isn't there a factor of 2? Because when I take 2 derivatives, you can think of that. Either both derivatives acting here, right? And that gives you 1 minus c. So that will give you 1 minus c times minus c, right? And that is what is coming out divided by z square. That is why it's giving you 1 minus c times minus c times the v. So that is part of that. But then 2 derivatives acting here, that is just that. But then there should be a term where one derivative acts here and one derivative acts here. But there's a factor of 2, right? Now why am I missing this factor of 2 here? That's my question. There should be a factor of 2. First derivative is this. Is that is correct? Minus c. But now the second derivative. What is going wrong? I don't. There should be a factor of 2 here. You see, I mean in this term. But why am I missing this here? Do you see anyone sees what is the problem? So what do I do? I'm taking a extra derivative. This is the first. Do we agree with that? The first derivative. Now I apply one more derivative. There are 2 possibilities. One, when it acts here, you get this. Of course, there's a v here. That's our problem. Yeah. Of course, there's a v there. Yeah. So there's a v here, and then there is one more term here, which is precisely 1 minus c over z dv by dz. Correct. And also there's a v here. That is a mistake. Yeah. So then then everything is fine. 2 times 1 minus c, and so this is 2 minus c. So this is 2 minus c. Okay. Good. Yeah. see, in fact, it was completely nonsensical to miss the v there, right? Otherwise, what is without v? Yeah. Okay. Now, what else I can say here? The behavior at infinity. Good. That's the next point. I mean, it will be interesting, right? Because here is the first time you are coming across a situation where there is an irregular singular point. Okay. So what happens near z equal to infinity? And for that, so at the moment, let's see, the most general solution that we have is this plus, so some alpha times this plus beta times second solution, which is z to the 1 minus c times phi a plus 1 minus c, 2 minus c, z. So this is the most general solution. I mean, these two are linearly independent solutions, and that's the most general. But the question is now, what is the behavior at infinity? Should I discuss now? Or? So, in fact, what you can do is that you define, let's define another solution, psi, a, b, c, z, psi, sorry, not a, b, psi, a, c, z, okay, which I will define through the same integral. This, sorry, I erased that. What was it? T to the a minus 1, t minus 1 to the power of c minus a minus 1, right? C minus a minus 1, e to the zt. Okay, but before we took the integral from 0 to 1, right? But now let's take the integral from 1 to infinity. In fact, 0 to infinity. Let's take 0 to infinity. Yeah. Let me take this integral from 0 to infinity. Okay. What is the 1 plus t? In fact, no, sorry. Minus infinity to 0. Minus infinity to 0. This is a definition which will times some constant. Okay? Again, some kappa tilde, let's say, some constant. Okay. This will be okay. I mean, again, if you look at the boundary term, so the boundary term is t to the a, t minus 1 to the c minus a, e to the zt. We want this to vanish, the two endpoints, right? This will be okay if if you look at the endpoint 0, this is fine if real A is positive, right? So if real A is positive, and now at infinity, if this would, I mean the dominant term would be this one, right? Exponential term, but it's e to the minus zt. So this will be exponentially suppressed provided real z is positive. So in that case, the boundary terms vanish, and then this will be fine. So for this situation where real A is positive and real Z is positive, this integral will be well defined. So this will also be another solution, right? Because I mean the adjoint operator anyway killed that. Only thing we had to make sure was the boundary terms vanish, and the boundary terms vanish for this. But so it has to be a linear combination of these two, right? So there should be some value of alpha and beta such that this solution is this is equal to that, some combination. Yeah. So how do we determine this thing, right? So let's try to determine it in the following way. For z equal to 0, so let's see. This is usually done by looking at the two. This has to be generally true for any z, right? So let's take for z close to z as z approaches 0, look at these two, and equate the two. You need two equations to determine two constants, alpha and beta, right? So one by looking at, say, as z goes to 0, and other you can look at as z goes to infinity, right? And then that should give the two contributions. So how you do this? So let me just try to first write down phi ABC, phi AC z. I mean the original phi AC z, which was, remember, the integral of the same integral 0 to 1 t to the a minus 1 or 1 minus t to the c minus a minus 1 e to the zt, right? This is the integral, and I will write this integral at times some constant k, which we knew already what the constant is. I can write this integral from minus infinity to 1, from 0 to 1, minus infinity to 0. Okay? I mean, this is simply, 0 to 1 is the same as minus infinity to 1 minus infinity to 0, right? This integral. And let's change some variable in these two integrals. So in the first integral, I change the variable t goes to 1 minus t divided by z. And in the second integral, I change the variable t going to minus t divided by z. Okay, you want t divided by z because this is e to the zt, right? So you want to get rid of the z from here. That's the reason for doing this. So that's why you change the variable t by z. Then this shift 1 is simply to make this 0. Okay, that's the reason. So then this integral, the first integral becomes okay, minus infinity to 1 when t is equal to 1. When t is equal to 1, this t is 0. So let me write t is equal to 1 minus t prime over z. Okay. So when t is equal to 1, t prime is 0, and when t is equal to minus infinity, t prime is plus infinity. Right. So this becomes 0 to infinity. Then there is a, actually it is infinity to 0, but then there is a minus in the measure, the change of the variable, right? dt is equal to minus t prime over z, minus dt prime over z. So that minus goes out, and there is a 1 over z coming from, this is dt. So there is a dt prime here. And then, so here you get 1 minus t prime over z to the a minus 1. And then here you get 1 minus t, which is t prime over z to the c minus a minus 1. And here you just get e to the 1, e to the z, which comes out of the integral. And then you get e to the minus t prime. Okay, that's the first integral. And the second integral is once again, so this is not t equal to, without the shift, without the shift. I mean that shift, remember, it was just to make this equal to 0. That's the reason I did that. So now here already when t equal to 0, t prime is 0, and when t equal to minus infinity, t prime equal to plus infinity. So this is again 0 to infinity. Again that minus sign is absorbed in the measure, and dt prime over z here. And then the rest of the stuff is simply t prime over z to the a minus 1, and 1 plus t prime over z to the c minus a minus 1. Okay? That is the result. Now you can see that this integral, this is exponentially diverging for the when z goes to plus infinity. Real part of z going to infinity. The exponentially diverging, which is the kind of behavior you see. So this means that that's what's happening near the regular singular point, irregular singular point. As z goes to infinity, this is exponential. So you remember, to study the behavior at infinity, you should take z equal to 1 over z prime, right? But then if you do that, this becomes e to the 1 over z prime, right? And when you make an expansion, this has arbitrary powers. So arbitrary power. So Laurent series. So it's an essential singularity here. See? So this is very, very singular as z goes to infinity. Yeah, that's one thing. So I mean, first thing, what you notice here is, I mean, this exponentially growing. That is not. I mean, that is just a power law for the z. Nothing. There's no exponential growth. So compared to that, you can ignore this. I mean, the real exponential growth is simply determined by that, right? And now you can even obtain exactly what it is. I mean, so after having taken that, if I want to look at the leading z behavior as z goes to infinity, leading z behaviors, I can just put z equal to infinity here in both of these things. And so there will be some overall power of z which will come here, right? As z goes to infinity, this term will be, you can ignore compared to that, right? And then this is dt prime, this is 1, and t prime to some power e to the minus t prime, but that is gamma function, right? That's related to gamma function. So in fact, you can get this expression, which is keeping also this constant, this kappa, which was we had evaluated. This was gamma, I don't know, gamma c over gamma a, gamma c minus a. I mean, this was determined by requiring that at z equal to 0, this is 1, right? So there is a kappa here. So after doing all that, so again, the logic was you take this kappa is that, you take the exponential thing and see the leading behavior there. So for leading behavior, I can ignore this term compared to 1 in z goes to infinity limit. Okay. There is some overall power of z prime, of z, which is actually we can see is a plus 1 minus c, but that 1 cancels. So this really, I can take this out. So this becomes simply z to the a minus c times this kappa. Okay. And then there is e to the z. And the second term, as I said, there's no exponential growth. So if I'm just looking at how fast it's exponentially growing, I can ignore the second integral. Everything is determined by that. And then this integral is simply a gamma function. Okay. What was the gamma function? Do you remember what was the gamma function definition? Unfortunately, I don't have those notes here. How did we define gamma function? Gamma of, say, z was t to the z minus 1, e to the minus t, 0 to infinity, right? This was the definition? So then you can see, so if once I ignore that, this becomes simply this becomes, I mean, that becomes, so including also kappa, so gamma c divided by gamma a, gamma c minus a, that's kappa. Then you have a z to the a minus c, e to the z. So this is the leading behavior. And the coefficient of that is simply t prime to the c minus a minus 1, e to the minus t. So this is simply gamma of c minus a, right? From this definition. Just replace z by c minus a. You get that? So actually gamma c minus a cancels. So you just have this coefficient. So what we are seeing is that the phi of a, c, z as z goes to infinity, a real z going to positive infinity, I mean the real z is positive infinity. In that case, it behaves like that. The exponential growth, very, that is a phi. What about the second solution? Second solution was z to the 1 minus c times phi. We just did that after making several mistakes. What was that? Yeah, a minus c plus 1, 2 minus c, z. Let us see how this will grow exponentially, the exponential term. Well, I mean, this was for arbitrary AC, right? So we just, instead of A, just take this. Instead of C, you just take that. So this will behave like, okay, there's a z to the 1 minus c. And then, well, e to the z, of course. And then z to the power of a minus c. But a now is that and c is that, right? So I will take the difference between these two. So what do you get? So c cancels when I take this minus that. 1 cancels with the 2, so minus 1, so a minus 1, right? So z to the a minus 1, okay, times what? Times gamma of this guy divided by gamma of that guy. So it's gamma of 2 minus c, gamma of a minus c plus 1. Okay. So notice again that this power of z is the same. You see, this guy was a. This first solution went like a minus c, z to the a minus c times e to the z. This one also, when you combine this prefactor with the asymptotic behavior of this phi, which is this, so these two things together gives you again a minus c. So both of them go like z to the a minus c times e to the z, but with different coefficients. One of them like that, other one with this coefficient. Okay. And finally, we need also the behavior of psi. Yeah, psi was the definition of psi. I mean, the psi was the other integral, right, which we defined. Psi was simply minus infinity to 0 of the same integrand, t to the a minus 1, 1 minus t, or 1 minus t to the c minus a minus 1, e to the zt dt. And this one, I mean, you can just, so again, change the variable. T goes to t equal to z over, t equal to t prime over z, or minus t prime over z. Then this becomes 0 to infinity because of the minus sign. And then you get dt prime. There is a 1 over z from here. And here you get z to the a minus 1 from there, t prime to the a minus 1. There are some overall minus 1 to some power. I'm not keeping track of that. So this is, let's say, goes like. This goes like. And then here you get 1 plus t prime over z to the c minus a minus 1. And then here you just get e to the minus t prime. Now this one, you see, has no exponential growth at all. Okay, there is no exponential growth in z. Okay. So this, when we said that this, of course, I can express psi. In fact, that is the reason for this psi. You see, I mean, both these solutions, this solution and that solution, we determine according to its behavior near z equal to 0, right? One of them was analytic, other was had this branch cut, z to the 1 minus c. But both these solutions exponentially diverge at infinity. Okay, so question is, in some physics problem, it may happen that you are looking for a solution which does not grow at infinity. Okay, which does not grow it, whereas both of these solutions grow exponentially at infinity. Okay. Now this psi, this particular combination is such that this does not grow exponentially. There is no exponential term here. Okay. So this may be interesting if you are looking for some physical solution of this equation which does not, which behaves, I mean, which does not diverge at infinity. No, you may be interested in something like that. In that case, it is this solution. But this solution, of course, will be a certain linear combination of them. But which linear combination? Well, it's clear that to get this, I better cancel these exponential terms. Both have exponential growth, so they have got to cancel, right? Which means that this means that this must be let's say some alpha. First one, the first solution, phi a c z plus beta z to the 1 minus c, the second. Which is a minus c plus 1, 2 minus c z. But I have to choose alpha and beta. Alpha and beta must be such that these leading terms cancel. So that already tells me the ratio of beta and alpha, right? Beta must be equal to minus alpha times gamma c over gamma a, and then times gamma of a minus c plus 1 divided by gamma 2 minus c, right? So that the exponential cancels. Now, of course, the precise alpha and beta I can fix by just taking z equal to 0, right? I mean, I have also freedom to, in fact, the way they have defined psi is not just by this, but putting a gamma also. I think there's an instance definition. There is a constant here, which that constant has been chosen to be 1 over gamma A. Okay, with again this is to normalize at z equal to 0, because let's see, at z equal to 0 this drops out, and then this is I mean, I don't know, one should check whether this is true or not. You know, I mean, okay, they have defined it like this, 1 over gamma A, this normalization. So now let's evaluate at z equal to 0 what happens. I mean, it's not so important, but I'm just if you want to get precise. I mean, here this gives you a ratio between beta and alpha, right? But if you want to really determine what are alpha and beta, you need one more equation, and that is obtained by setting at z equal to 0, right? You can evaluate this at z equal to 0. Here z equal to 0, both phi and this phi and that phi are is 1, right? Again, assuming the real part of 1 minus c is positive, this drops out at z equal to 0, so you just get alpha, right? So left hand side is just alpha. So if you can evaluate this, what happens at z equal to 0, then you are done, right? So to get this expression for z equal to 0, what you do, z equal to 0, this integral is minus infinity to 0, t to the a minus 1 times 1 minus t to the c minus a minus 1. Okay, there is just 1 over gamma A, and you can do it, I think, in different ways. You see, I mean, this should be related to beta function after all, right? Provided I can, for beta function, the integral was 0 to 1, right? So I have to make some change of variable such that, say, one of them stays 0, other guy goes to 1, right? So I could, how shall we do it? If you have, suppose, 1 over t at infinity will be mapped to, no, that is no good. How can I do this? So I want to map, or you can split this integral. You know, first of all, change a variable. Let's see, make it 0 to infinity, and then split the integral from 0 to 1 and 1 to infinity, right? And then from 1 to infinity, you take t to 1 over t, which again maps to 0 to 1. But I think it should be possible to directly do it. Maybe I'll just stop. But I mean, you know, you change some variable to some variable, say t prime, such that when t goes to minus infinity, t prime goes to, say, 0 or 1, and when t goes to 0, t prime goes to other one. So instead of these things, you want to take it to 0, 1, right? Maybe I'll just leave this now. Leave this as an exercise, and next time we'll do it. It's a change of variable. I mean, generally by SL2 transformations, you know that 3 points can be removed, make to another 3 points. Here it's even much less requirement. Here we are saying just take 2 points and move it to 0 and 1. So with the standard procedure, you should be able to get that. And then this will become some beta function, and yeah. All right. So I think I'll stop now. This is basically the discussion of confluent, and now we'll show that all these Hermite polynomials, Laguerre polynomials are related to confluent next time, and we'll discuss Bessel function. Those are the important things. Yeah.